Hi, welcome to BOZ8. Today, we will discuss the question, how would you approach improving the robustness and reliability of a deep learning model deployed in a real-world environment where the data distribution is constantly changing? Here is the content. In deep learning, robustness refers to a model's ability to handle new, unseen data without significant drops in performance. Reliability is about maintaining consistent predictions over time, especially in real-world environments where data conditions often change. Real-world deployment adds complexity as the data distribution can evolve over time, resulting in issues like dataset shift, where the statistical properties of input data shift, making the model less effective. This challenge is widespread, affecting applications in e-commerce, finance, healthcare, and autonomous systems, where models need to perform reliably despite fluctuations in input data quality, noise, or imbalances. Dataset shift can be categorized into three main types. Covariate shift occurs when the distribution of the input features changes over time. For example, new sensors or changes in environmental conditions may result in different feature distributions. Label shift happens when the distribution of the target labels changes. For instance, if the distribution of classes in a classification task changes, the model may no longer predict with the same level of accuracy. Concept shift is a more complex form of shift, where the relationship between the features and the target changes. For example, in fraud detection, new fraudulent patterns might emerge that the model was not trained to recognize. Understanding the type of shift is crucial because different strategies are required for handling them. For instance, covariate shift may be handled by adjusting the model or retraining it on updated data. Improving robustness requires the model to generalize well and adapt to new data distributions. Some of the strategies include data augmentation, introduce variations in the training data by augmenting it with noise, transformations, or synthetic data. This can help the model learn to recognize patterns in a variety of situations. Regularization techniques like dropout or L2 regularization reduce the likelihood of overfitting to noisy or limited data, thereby improving generalization. Ensemble methods. Combining multiple models can help reduce the likelihood of errors. For instance, bagging or boosting methods can be used to create stronger models that are less sensitive to fluctuations in the data. Adversarial training. This involves training the model on data that has been intentionally perturbed, enabling it to learn to deal with small changes or noise in real-world data. One key way to maintain robustness over time is through retraining and continual learning. Incremental learning allows the model to update as new data arrives without retraining from scratch. This can help handle gradual changes in the data distribution without requiring a full retraining cycle. Online learning processes data in a stream, updating the model as new instances become available. This is useful in environments where data is constantly evolving. Transfer learning helps when shifting to a new domain or task. By reusing a model trained on one dataset and fine-tuning it with a smaller amount of new data, it becomes more adaptable to changes in the environment. Periodic retraining is crucial to keep the model's performance consistent. The model should be retrained periodically using the latest data, especially in situations with substantial shifts in the data. Monitoring model performance is essential to ensure the system behaves as expected after deployment. Continuous tracking allows teams to detect problems before they lead to significant failures. Continuous monitoring. The model's performance should be tracked over time to ensure it is consistently performing at the expected level. Any significant deviation could indicate a shift in data or an issue with the model. Performance metrics. Regularly evaluate the model using common metrics like accuracy, precision, recall, and F1 score, and ensure that the model meets the required thresholds. Real-time feedback loops. In some applications, Real-time monitoring allows adjustments to be made on the fly, enabling the system to adapt more quickly to changes in data distribution. Anomaly detection. Set up automated mechanisms to detect performance drops or anomalies in the model's behavior, alerting the team to possible data shifts or other issues. Model drift refers to the gradual change in model performance due to a change in the input data distribution. This is common in real-world applications and needs to be actively managed. Drift detection algorithms. Statistical tests like KS tests, chi-squared tests, or specialized algorithms in tools like Alibi Detect or Scikit Multiflow can identify when a model's performance is significantly affected by changes in input data. Adaptive models. Once drift is detected, the model can be retrained or adjusted to account for new patterns. Techniques such as ensemble models or online learning can help quickly adapt to changing distributions. The goal is to minimize the performance degradation while maintaining the model's responsiveness to data shifts. Dealing with noisy data is crucial for maintaining model robustness, as real-world data often contains errors or irrelevant information. Pre-processing techniques. Handling noisy data involves identifying and correcting issues such as missing values, outliers, or inconsistent data points using methods like imputation or outlier detection. Robust training. Methods such as robust loss functions can be employed during training to reduce the impact of noisy data on the model's learning process. These loss functions are less sensitive to large errors or outliers. Noise regularization. Techniques like dropout or noise injection during training encourage the model to learn more generalized features, which helps it ignore irrelevant noise during inference. Incorporating external data sources can help improve robustness, especially when real-world data is insufficient or unreliable. External data. This can include domain-specific data sets that provide additional context or data diversity, improving model generalization. Synthetic data. When real data is scarce, generating synthetic data can help augment the training process and expose the model to various scenarios. Transfer learning. Leverage pre-trained models or knowledge from similar domains to improve robustness when transitioning to new tasks or environments. Cross-domain adaptation. Techniques like domain adaptation allow a model trained in one domain to adapt to another, reducing the impact of distribution changes in new environments. Testing in simulated environments is a critical part of ensuring that the model will perform reliably in real-world conditions. Simulated environments allow for controlled testing where edge cases and rare events can be simulated, enabling identification of potential model weaknesses. Stress testing challenges the model's robustness by exposing it to extreme conditions and outliers that might not be encountered frequently, but are important for reliability. A/B testing can be used in production to compare new models against existing ones, evaluating their performance under real-world conditions. Model validation ensures the model has been tested under all potential scenarios, improving its resilience when deployed. To ensure robustness and reliability, continuous attention must be given to both data quality and the evolving environment. Focus on data. Ensuring the data is of high quality, representative, and free from bias is crucial for building a robust model. Continuous monitoring. By setting up